Okay, good afternoon everybody and welcome to the August webinar from Alarm Corp. My name is Piotr Tolecki. I'm the National Product Manager CCTV at Alarm Corp, and today's topic is CCTV Fundamentals, Network Video Systems Design. Some of you may have attended an Alarm Corp webinar before, others have not, so just to get everybody up to speed, let's just go through some of the housekeeping. Now, if you've not used the GoToMeeting screen before, you will see this on the right of your screen. First of all, you will see your own name. Next, you will see that you are all muted for the duration of the webinar. We will be taking questions at the end. Now, just to verify that you can all hear me, can I please get you to press the raised hand icon? Okay, great. I see a few hands going up. Perfect. Thank you very much. If you can put your hands down. Okay, next. There is a questions tab underneath the audio. You are free to type in questions at any time during the presentation. I will be going through the questions at the end in the order that I receive them. Now, just so you know, the questions are confidential. Only I get to see who asks the questions, so don't be shy. Nobody else will know who is asking. So once you have typed in a question, just make sure you press the send button at the bottom. Okay, with the housekeeping out of the way, let's get started. Today's topic is on network video or network video systems design. And we will be covering some of the following. A bit of terminology and concepts just to get everybody clear, specifically edge recording and central recording, why a video network is different to a normal TCP IP network, some of the bandwidth issues to consider, and some other design considerations, and finally some conclusions. Okay, let's get started. A little bit of terminology just to make sure we're all talking on the same wavelength. When we talk about network video and network video systems design, we can talk about edge devices. Now, edge devices are typically devices out in the field. They can be cameras, typically IP cameras. They can be encoders used to convert analog cameras into IP. And of course, they can be some of the field-mounted IP network switches, as well as any remote workstations. And in this context, even an iPhone could be considered an edge device in that it may be used to view the network from the edge or from the field. Next, when we talk about core or central devices, so obviously the main or backbone switches, any NVRs or servers, and I would also class the main workstation, typically used by the security manager or the main systems administrator, as a core device. Okay, edge recording. Edge recording means we are talking about recording to either the built-in storage on a camera, and this will typically be an SD card or micro SD card, and also recording to a local DVR in the field. For example, a Fast Trace 2 or even the older AdPro Fast Traces, a smaller TrueVision TVR10. Central recording, on the other hand, is we are streaming all of the IP streams back to the central location, and we are performing all of the recording at the central location. And a good example of this would be a Nextiva master recorder VMS running on a Dell server with or without iSCSI attached, direct attached storage. Now, there are both benefits and disadvantages to both edge recording and central recording, and I thought it'd be worthwhile just to discuss some of these because they can have a bearing on how you would plan a network video system. Okay, so first of all, let's look at the benefits of edge recording. First and foremost, if we have any local storage at the camera or even with a local DVR, we have redundancy in case the network link fails or is congested. Likewise, we can reduce the uplink bandwidth required, and this would be typically used if we have a megapixel camera and we record in full megapixel resolution locally, but we stream back to central, let's say CIF or 4CIF. Now, this is very useful for pre- and post-alarm recording. In other words, you may be streaming a reduced stream all the time to the central location, but recording on event on a motion event or on an alarm event at full resolution locally at the camera. And this is also very good where any off-site viewing or from the central location is done by exception. In other words, you're not viewing live video all the time. You only want to view video in case there has been an event or an alert at the site. Likewise, this is a good approach to use where the bandwidth is not available or is cost prohibitive. So typical applications for edge recording might be remote sites or campuses where the uplink back to the central location is either ADSL, 3G or wireless LAN, which does not have the full bandwidth. And examples of edge recording, you might have a Variant 5120 dome camera with built-in SD card storage. Some of the Interlogic's TrueVision IP cameras also have SD storage. So that's typical edge storage at the camera. Or you might have an Xtralis FT2 or a Variant Edge VR. So just to illustrate the point, if you have field devices and the network link is severed, you can still record locally even though the streams cannot make it back to the central location. So this is where this concept of redundancy comes in. Okay. We've talked about the advantages of edge recording. Now let's talk about the disadvantages. First of all, the physical security of the remote device, the actual location risk. If we have a camera out in the field, we have the risk of theft of the camera, of vandalism. We can also have natural disasters, fire, flash flood, lightning strike. With predictable results if the camera with SD card storage gets damaged. Okay. Likewise, there is the issue of retention time. Now, as of today, the typically biggest SD card that you can readily buy is up to about 32 gigabytes versus many terabytes on a central server. There is also the physical longevity of the recording medium. In other words, can an SD card deliver the same number of read-write cycles, and how long will it live in a camera that's sitting on top of a pole that's regularly getting to very high temperatures because of direct sunlight? Next, there is the issue of access to retrieve incident footage. If the site is physically distant, then we have the issue of travel time to and from site. Commensurate with that is the response time. If you know you've got a fairly small SD card on site, then you need to get to that site pretty quickly to retrieve the footage before that footage is overwritten. Next, what about specialist equipment? If you have a camera up on a pole in a jail or on an airport perimeter, you may need a cherry picker, you may need safety harnesses. If it happens to be a camera in a freeway tunnel, do you need to shut down the tunnel? Do you need to lock down the jail, etc.? So the impact on site may not be insignificant. Next, the cost per gigabyte is typically much higher with edge storage than centralized. If you look at now a 1 terabyte hard drive, you can be had for under $100, whereas a 32 gigabyte SD card is still around the $30 mark. And finally, we have the issue of maintenance. Unless your edge device will automatically alert that the storage media is failing or has been removed, you need some proactive health checks to verify that the edge device is still recording. Okay. Now let's talk about the advantages of central recording. First of all, physical security. If you have a dedicated equipment room or dedicated server room, it's typically under lock and key. It will typically have air conditioning and fire protection. You will typically have a lot less dust buildup in a central location. You will typically have a UPS or a generator backup. So hence the risk of equipment theft, vandalism, or other damage, including environmental damage, flash fire, flood, etc., is probably lower. Now, the storage in a central location will typically be either RAID 5 or network-attached storage, which offers better redundancy. A single hard drive failing in a central location is unlikely to cause data loss, which is not the case on site if a single SD card fails. And finally, the personal response time is also typically much lower. Next, retention time and storage costs. We can have much larger storage sizes possible with central recording. To give you an example, a Dell MD1200 PowerVault can handle up to 36 terabytes on board versus a 32 gig SD card. So we can achieve much longer storage time. And as we discussed earlier, the cost per gigabyte is typically lower than at the edge. And finally, serviceability. Physical access to the central location is normally much easier than remote sites, and you're less likely to need cherry pickers, safety harnesses, scissor lifts, etc. Okay, so we've talked about edge recording and central recording and what were the benefits and disadvantages of each approach. Now let's talk about what makes a network video, or a video that's intended for a network that's intended for streaming video, different. Okay, isn't all IP traffic the same? Why is a network video different? Well, there are a number of points to consider. Video traffic has some particular needs. Unlike FTP or emails or even print jobs, video traffic is time critical. First of all, we need the absolute minimum transit time, or latency, and we will talk about latency a little bit more. Secondly, video packets need to arrive in the right order. Third, video bandwidth is used 24/7. Now, delays in video packets can make the image unusable. On any network, you can have issues of congestion, packets getting lost due to packet collisions, etc. If you're sending an email and the email gets, you have packets lost, it's easy enough for the receiving network server to request a packet to be resent. Now, because an email message is a final length, you can keep resending that packet until it makes it through. However, with a video stream, you have a finite size sending buffer, and that buffer keeps getting refilled with new video frames, because in effect the video stream is infinite. It doesn't just stop. So if a packet gets lost and you cannot retransmit it in the time before the buffer gets overwritten, that video packet gets lost, and the net effect is that you can have image dropouts, and you can actually have an unusable video image back at the receiving station. So, for video traffic, we need very consistent, predictable paths through the network. And this is where we have a bit of a problem, because the Ethernet network was intended to be very good at redirecting IP traffic if particular paths get congested. And an example of this is the spanning tree protocol. Now, as we said earlier, packets can arrive out of sequence at the destination. Now, this is a big, big problem for video traffic. As we said earlier, if packets are received in the wrong sequence and cannot be reconstituted before a next batch of packets, we have an image loss. Now, we said we need the shortest possible path. Every additional hop in a network adds latency. And this is particularly noticeable if we are trying to do pan-tilt zoom cameras and trying to control the cameras in real time. Okay, now here we have a very basic, very simple video over IP system. We've got a few cameras out in the field. We have a mix of IP cameras. We've got an analog camera with an encoder, and we've got a few switches. And finally, back at the central location, we have a network video recorder, and we have a client workstation. Now, typically in these system drawings, the IP network is shown as a cloud, and we don't delve too much into the details of what actually is inside that cloud. Well, this time, let's go into it in a bit more depth. Okay, here we have a more detailed view of the cloud, and we can see here that because of this network topology, we have a number of possible paths for a packet to come through. So let's say we're sending a packet from edge device A to a central device, which are shown here. And you can see straight away we have a number of paths possible. Obviously, we can go straight down the middle path, which is the simplest path with only the two switches, one at the edge and one at the central location. But if this path gets blocked, we can go this way, which adds an extra hop, and finally we can go this way, which also adds an extra hop. Now, the key point here is that the various packets can get redirected over the various paths on a dynamic basis. Most switches do try and do some sort of load balancing, and unless this is managed and factored into the video system design, we can end up with video packets arriving at the destination out of sequence. Okay, so let's talk about some of the key considerations for video over IP. Let's talk about some bandwidth issues. First of all, if we have a standard definition camera running at 4CIF, running fairly modern H.264 compression, and we are running this camera real-time at around 25 images per second, depending on the compression settings and the exact codec, we are running anywhere between 1 and 2 megabits per second. Once we go up to a megapixel camera, we are running at anywhere between 4 and 8 megabits per second, up to about 5 megapixel resolution. So if we have 16 standard definition cameras, we're running 32 megabits per second. If we have 16 megapixel cameras, we might have 128 megabits per second being used. And if we have permanent streaming, viewing or recording, then this bandwidth is used on a 24/7 non-stop basis. Okay, when actually designing a network topology, we also need to remember the power supply. Most fixed IP cameras are PoE capable. Now the benefit of that is we eliminate the need for dedicated power supplies. However, we need to check that a PoE capable switch has a suitable power budget. In other words, if we plan on connecting 24 cameras to a PoE switch, can this switch supply power to all cameras simultaneously? Now most good switches will, however some switches will say on the data sheet, oh, you need an external power supply to achieve this. Now, most PTZ cameras will still need dedicated power because their power needs will exceed what's possible over PoE. Now, don't forget, the maximum length of a LAN cable is about 90 meters. In other words, we need to factor this into the system design. We need to make sure that all of our cameras are within 90 meters of a PoE switch, or in fact within 90 meters of any switch, if we are running over Cat5 or Cat6. Now we touched on latency a bit earlier. It takes time to encode the video, to transmit the video, then to decode and display the video. Now the latency will obviously depend on the hardware, how quickly the streaming camera can encode the video, and also how quickly the decoding station can decode the video. But also on network topology, the more hops we have, the more switches we pass through, the more latency it adds. Because remember, most switches have what's called a store and forward application. In other words, they receive the packet and then they retransmit it. Now, latency may be critical for real-time applications with PTZ control. So that also has to be factored into the system design. And it may be that different network topology is needed for any PTZ cameras as opposed to any fixed cameras. Some more key considerations. We need to look at network issues and data security. Now, if we are talking about new networks, it's fair to say most new networks will be installed as gigabit. But if we're talking about incorporating systems on a legacy network, you may well have 100 megabit LANs. Now, 100 megabit LANs are okay at the edge, and they will be okay for smaller systems. But once you start picking up the cameras and streaming back to the central location, that backbone needs to be gigabit. And this really needs to be planned because this is the critical component. Now again, if we're talking about sharing video on an existing corporate LAN, in other words, we've got an existing LAN and we want to add some IP cameras to it. This is seldom viable. We really need a separate LAN because, as we said earlier, quality of service is critical for video. Video packets must have absolute priority and guaranteed stream integrity to give us a reliable and stable image stream. Now, if we go and do this on an existing LAN, what impact will this have on current users and on the current system? This also needs to be considered. Next, who can access the video stream and storage? And here we're talking about both physical access to the actual server room, who can physically access the network to unplug cables or unplug equipment, and who can access it remotely via the web client or web browser or any configuration software. We need to look at the impact of firewalls, because some VMSs need to have firewalls switched off for reliable operation. And if that's the case, then we need to make sure that the network is secured by other means. Packet sniffing. We need to look at MAC address level security. For example, we may wish to deny or allow access of particular devices to the network based on MAC address. If not, is it possible for somebody to substitute the stream? What about denial of service? Can somebody put on a duplicate IP address onto the network to force a camera offline, etc., etc. When we look at all of these issues, we really need to be clear on who owns the network, who is responsible. Is the network owned by the security company or the security manager, or is it owned by the IT team? And this is not a trivial question. And quite often on any bigger system, in any bigger organization, this will be the single biggest question or the single biggest factor in determining whether or not a network video implementation goes smoothly or not smoothly. Okay, now let's do some planning for bandwidth. How much bandwidth do I need? And this decision will affect both the information technology and security. Likewise, it will affect the cost of the infrastructure and image usability. Now, partially this stems from the choice of cameras, resolution, and frame rate. Now, typically this is a security issue. What resolution do I want? How many images per second? Whether I want standard cameras or whether I want megapixel cameras. But once we plan on putting these cameras on the network, the security issue pretty quickly becomes an IT issue. Now we have recording calculators available for most IP cameras and network video recorders. And on the next slide, I'm going to show you some example recording calculators. This is an example of a Variant Nextiva calculator. And we see here that if we have a fixed dome or body camera, we're running it at 4 CIF, and we're running it at 12.5 images per second, then our typical bit rate is going to be at around the 616 to 880 kilobits per second, which we can see there in the first column between the red lines. On the other hand, if we have a same resolution camera, but suddenly it's a PTZ with more motion in the image, we can see now that the average bit rate is slightly higher, and we will go into that in a bit more detail shortly. So you can see here in this example where we have a total of 68 fixed cameras, 2 PTZs, and some spare capacity. If you look at the very bottom right-hand corner, you'll see that our total throughput is approximately 5.7 megabytes per second for a total storage of about 14.6 terabytes. So this is just one example that shows you, depending on what camera resolution you pick and what frame rate you pick, as to what bandwidth you will end up with. Next, here we have an example of a NVR20 recording calculator. This is for the Interlogic TrueVision NVR20, and you can see here we have some examples. If we have a 2 megapixel camera running at full resolution, 1600 by 1200 at 12 frames per second, there straight away we're up at 4096 kilobits per second, so just on 4 megabits per second. You can see if we go down to row 14, we have a 5 megapixel camera, and if we run that at 2560 by 1920, which is the full resolution, we are up at over 7 megabits per second. However, if we go down to a standard resolution camera and we run it at VGA resolution, which is row 12, you can see we are down at 768 kilobits per second. So I guess the whole point of showing you this recording calculator is that depending on what cameras we pick, what resolution we want to stream at, and what frame rate we want to stream at, this has a huge bearing on the network bandwidth that we will be using. Okay. When we talk about compression and bandwidth planning, on many cameras and on many encoders, we have the option of using either constant bitrate or variable bitrate, CBR and DBR for short. Now let's explore this a little bit more, because this also has a big bearing on what happens with our bandwidth. Some of you, or most of you hopefully, will remember that not that long ago we were using MJPEG compression for most IP cameras. Now MJPEG is not as efficient as H.264, but it is more consistent because each frame we send is a full frame. So in some ways MJPEG was a little bit easier to plan for. On the other hand, H.264 is conditional refresh. We have complete iframes with smaller predictive frames. So what that means is that the peak bandwidth can be much higher than average bandwidth. Now, with a constant bitrate approach, the compression algorithm attempts to smooth out the bandwidth by varying the compression at the expense of quality. On the other hand, variable bitrate allows the quality to remain pretty constant, but allows the bandwidth to vary. And you can see here in this example image where the relative motion inside the image is quite low. With variable bitrate, the actual bitrate used is lower. However, as motion becomes higher, then with variable bitrate, the actual bitrate required becomes higher and higher. And to give you another example of this, okay, here we have an image showing constant bitrate, and hopefully you can see in the image that there are a lot of artifacts and that therefore the quality is being compromised in some areas of the image. However, note also on the graph below that we have a fairly consistent bandwidth of around about 0.52, peaking at around 0.67 megabits per second. Sorry. Okay, and we can see up in the table below the average bitrate is about 0.6. Now, if we go to variable bitrate, straight away you should see that the image quality is much higher. However, notice that the bandwidth is now peaking at over 1.1 megabits per second, and it is a lot more variable. So, this is the difference between constant bitrate and variable bitrate. So which do we choose? How do we select? And what do we size the link at? Do we pick it for the maximum bandwidth or do we pick it for the average bandwidth? Now in this context the link can refer to an ADSL connection, or it can even be the internal link on a LAN if we're talking about sizing up a quality of service rule. Now if we size the link for the maximum likely bitrate or the maximum likely bandwidth, we will get better performance, but it's likely to cost more, particularly if we're talking about an ADSL pipe. Now, if we size the link for an average bandwidth, this is likely to be more cost-effective, but it's likely to cause occasional image issues, as we saw in the preceding images. So this may require fine-tuning during commissioning. Now, hopefully, once we have remote bandwidth up to the full national broadband network standard, then this will not become such an issue. But at the moment, with many remote sites still running over ADSL, this is still an important design consideration. Likewise, it is an important design consideration if we're talking about putting video over IP systems onto existing legacy networks. Okay, a little bit on network switches. Not all network switches are created equal. Obviously, we have to look at the number of cameras or camera ports required at each given switch location. Now, PoE or local power, encoders or PTZ cameras. If we have a PoE switch, what is the switch's PoE budget and how many ports are actually PoE? You may find that on some smaller switches, you might have an 8-port switch, but only 4 of the ports are PoE capable. The rest are not. Now, will this switch need any additional power modules to deliver the full PoE power? Some switches do, some don't. This is where it pays to really check the datasheet of the proposed switch. What is the maximum throughput, or the switch fabric as it's referred to on the switch datasheets? Next, how many uplink ports does the switch have? Can these be aggregated? And you will find on some switches you might have either 2 or 4 gigabit uplink ports, and on many of the managed switches it's possible to aggregate these ports. The net result is you end up with a single 4 gigabit uplink. Next, if we know we have longer runs, are we using any optic fiber backbones? Therefore, have we picked the right SFP small form factor pluggable modules? And in this case we need to check, are we running single mode, are we running multi-mode? And you see here again a couple of switches which shows the uplink ports which can be aggregated on these larger switches. Okay, if we're talking about advanced storage concepts, what is the storage concept? Are we talking about direct attached storage, in other words an iSCSI device hanging off the back of our network server or our network video recorder, or are we streaming all of the streams onto a network attached storage? If it is network storage, is it on-site or off-site? Are we going to be using fiber channel switches? If so, have we picked the right fiber channel switch? If we are using fiber channel, we need to make sure that we've got allowed for the right patch cables and the right connections when we actually plan and design the network. Network topology. We need to have an understanding. Are we planning a brand new network, or are we integrating into an existing network? Will the surveillance network be isolated from other traffic? Next, do any third parties control any part of the network? For example, if we have ADSL, is this controlled by a telco or an Ethernet service provider? Likewise for 3G or any GSM uplinks. The physical distances between switches. Will we need to use any optic fiber? And again, here we have an example of a typical network implementation. In this case, we know we have a fiber backbone, and you see here we have a mix of both direct attached storage hanging off the master recorders, and we also may have some offsite storage running off a network attached storage or SAN. Okay. Finally, security and passwords. We've talked a lot about bandwidth, we talked a lot about bit rates and so forth, but don't forget, once we have any network in place, we need to also take care of the fundamental housekeeping. Remote access to any DVR or camera often requires that the devices are on a public address. If that's the case, have we made sure that the login credentials have been changed from their default, e.g. admin? If the passwords have been changed, who keeps the details? If that person leaves the company or is hit by a bus, who else knows? Now, this is not a trivial issue because resetting any lost passwords may be problematic. You may need to return the unit back to the factory or supplier. You may need to have the technician out on site at a particular date and time, even if it's just to push a reset button on the back of the camera. And if you do reset the camera, it's back at the factory defaults, then you need to reprogram it and typically re-add it to the system. You may need to uninstall and reinstall the management software. And you may even need to rebuild the server or workstation. Now, none of these things are not impossible. They're all possible, but they may be time-consuming. So again, this is an important factor to consider with any network video system. Okay, some conclusions. When we are designing a network video system, we really need to plan carefully, understand the bandwidth requirements, understand the requirements and limitations of the proposed devices, understand the limitations of any existing network infrastructure, understand the impact any decision such as bandwidth or streaming or frame rates will have on the usability and quality of the image that we're trying to stream and record. And finally, we need to understand who the key stakeholders are, particularly when working with or on existing or shared networks. Okay, would you like to know more? More information, including brochures and data sheets, may be found at www.alarmcorp.com.au. If you haven't already, I would urge you to subscribe to the Alarm Corp Pulse to receive new product information automatically. You can register online to get full access to our e-commerce platform, including pricing and order placement. Contact your nearest Alarmcom representative, Jeff Rushton and Diane Brazil in New South Wales, Stephen Dinger in Victoria, SA and WA, or myself, Piotr Toletsky, on 0421 378 334, or email me at prd@alarmcorp.com.au. Now, if you've enjoyed this webinar, we will have more webinars for the remainder of 2012. These will be every month on a Wednesday at 2 p.m. and additional topics planned for this year include the iPhone as a surveillance tool and optimizing DVR configuration. Go to our website and click on the resources for a full list of the topics. We look forward to your participation. Okay, if you haven't done so in a while, please visit our website. We always have regular specials and updates. And with that out of the way, now over to question time. Please feel free to type in your questions. Don't forget to hit send. Hit send at the bottom, and I will go to the questions in the order that they are received at. Over to you. Thank you. Okay, the first question I've been asked is on storage and bandwidth calculators. how reliable they are. Again, most recording calculators uses maths. It provides a valid answer provided that the input is valid. There are some differences you might find, for example, if you use exactly the same parameters on, say, a variant storage calculator, and then you take an error count storage calculator, you might get two different answers. And again, that will stem from the fact that the two different cameras use a different implementation of the codec. So one might be compressing the video more, one might be compressing the video less. So yes, typically there will be some differences. Okay. Okay, what did you mean by aggregate when you were talking about network switches? Good question. On some managed network switches, and an example of this would be either the IFS network switches or some of the Dell Power Connect gigabit switches, is you may have 24 ports and you may have a separate 2 or 4 uplink ports. In the case of, say, a 24-port PoE switch, the 24 PoE ports are 100 megabits, whereas the 2 or 4 uplink ports are full gigabit. You can actually configure those ports to work as one logical port. So in other words, it's like having 2 or 4 lines all sharing traffic back to the one address. So this is what we mean by aggregating the uplink port so that it becomes a larger virtual port. And this is very useful, for example, if we connect the 2 uplink ports in parallel back to the same network switch. And the benefit of this is we gain increased bandwidth over if we were just running a single unaggregated port. Okay. Are the products open platform? Again, a good question. The answer is it depends. If you look at most IP video manufacturers today, they will have a range of on-with capable cameras. They will have a range of on-with capable recorders, but some of the functionality is proprietary. So you might find if you run a camera, a third-party camera with a particular NVR using on-with, you may not get this full functionality that you would if you were, say, running that camera with its own proprietary VMS. So it depends. It really does depend on the system in question. Okay, next question I've been asked that is, does Alarm Corp stock and can Alarm Corp demonstrate some of this equipment? The answer is yes, we can. We have a number of systems set up in both our Melbourne showroom and in our Sydney showroom. So we have examples of megapixel cameras. We have example of remote client management client software. So again, I would urge you to contact your nearest relevant Alarm Corp state representative for a rundown of what's possible and to arrange a meeting. Also,